I'll talk today about the modeling of physical processes in the solar wind in local interstellar medium, simulations supported by the NSF-PREC project and ran on blue waters. So this is a list of my collaborators over here. So first of all, I will focus on the key challenges of this problem. It's from the general perspectives, it looks like a simple problem. Two streams interact. There is a stream of interstellar medium plasma which interacts with a stream of the solar wind plasma. From the MAG perspective, they collide, form a tangential discontinuity, which is called the Heliopools, right here, HP. Since the motion of the solar system through the interstellar medium is supersonic, and probably it's also super fast magnetosonic, there is a possibility to have a shock wave in front of the Heliopools. We definitely know for sure, because it was measured, that there is a heliospheric termination shock when Voyager spacecraft crossed it, so we know for sure. And this figure shows the general pattern of the interaction. The interstellar medium flow is from the right to the left. The sun is the origin, and these different colors, they correspond. This is, first of all, magnetic out-of-plane component of magnetic field shown here. And because the polarity of the solar wind changes every 11 years, so we see those patches in the magnetic field direction. So the problem is that interstellar medium is partially analyzed, ionized, so we have a lot of neutral particles over there. Neutral particles penetrate into the solar wind, charge exchange occurs, neutrals becomes an ion, but this ion is non-thermal ion. It will never become thermal, okay? So then you create neutral particles, new neutral particles during this interaction. And these neutral particles can propagate far upstream and actually affect the local interstellar medium. These particles are called neutral solar wind. So from this perspective, the bow wave you see in front of the Heliopools, it is highly modified by charge exchange with neutral solar wind. So you will never know whether there is a shock or not, only knowing the properties of the interstellar medium. So pickup ions are also non-thermal and should be modeled appropriately. Charge exchange is infrequent. Charge exchange occurs at roughly every 15 astronomical units. And so from the perspective of this simulation, neutral particles should be modeled kinetically. So we solve MHD equations coupled with kinetic Boltzmann equation for neutral particles. For pickup ions, non-thermal ions, we use different approaches. One of them is based on the fluid approach, where it is assumed that they co-move with solar wind plasma. And so we need only to solve the pressure and continuity equations for them. This is actually a very good thing, just to treat them as a separate fluid because of the charge exchange properties depend on energy. And so right here you see two simulations. One of them shows the plasma distribution, again, in the solar wind interstellar medium direction. This is termination shock, Heliopools, termination shock, Heliopools. But one of the solutions is in the, this one, when pickup ions are treated separately. But otherwise, if they're not treated separately, they become part of the mixture. And so some average temperature is established. It was found out that in this case, the termination shock goes further from the sun, the Heliopools moves closer to the sun, so the width of the heliosheath can be different. Another approach is to actually model the pickup ion properties, the distribution function as it propagates, pickup ions propagate outwards. And this is a very good thing, except that it becomes not possible across shocks, because in these equations become so complicated that there will be not enough time to solve them. So then we try to derive proper boundary conditions across the shock for pickup ions and use them instead of approximating equations across the shock. So our simulations are data-driven, and on the other hand, they are validated by observations. So the boundary conditions in the solar wind are pretty much uncertain, but we use the best we can. The interstellar medium properties are known much better now, and this is because, first of all, of voyagers crossing the Heliopools and measuring the properties of the interstellar medium, but also Interstellar Boundary Explorer, another spacecraft, is measuring the properties of neutral particles, which depend on the properties of the solar wind and stellar medium interaction. And so by adjusting the properties of the boundary conditions in the interstellar medium and reproducing the IBEX data, we sort of constrain our models. Recently, there is also hydrogen deflection plane issue just measured by SOHO, and recently the anisotropy of 1 to 10 TeV cosmic rays, it turned out that the properties of the heliosphere are very well seen in the anisotropy, flux anisotropies. Solar wind simulations are important from Earth's surface to Earth, are important for space weather predictions. And all these simulations we do using our multi-scale fluid kinetic simulation suite, which was initially supported its development by the NSF ITR project many years ago, but then by multiple NASA projects. This is a general block scheme of the suite, but in principle, I told you everything. So we solve MHD equations coupled either with multiple Euler system or with kinetic Boltzmann system. Why it matters? First of all, we have voyagers, and which are they were performing a lot of in situ measurements in the solar wind by then, both now in the interstellar medium. And this is a mission which is more than 45-year-old, and they provide in situ measurements of the interstellar medium, which is unbelievable. Yes. So it's just fantastic, and from the astrophysical perspective, we are talking with astrophysicists that they should just try to somehow adjust their views with what is now measured in situ and will not be measured in situ for many, many years afterwards. Okay? Interstellar Boundary Explorer is measured energetic neutral particles. Energetic neutral particles return to the detector, but they are created in charge exchange of non-thermal ions with interstellar medium neutral atoms. So it was found out, it really was fantastic discovery of the very bright ribbon, they called it a ribbon, sorry, a ribbon of enhanced ENA flux in different energy bands, actually, on the all-sky map. So the increase, just very narrow, but 3 times higher flux of energetic neutral particles. We proposed a mechanism and for these responsible for this ribbon, and just not only we proposed it, we I think our group is the only one which is actually performing simulations where we use the IBEX ribbon as a constraint for our model. So it's just to find the ribbon fluxes, it's a separate kinetic problem itself, and that's very interesting. So recently launched in the summer of 2018, the Parker Solar Probe is just another fantastic mission which successively spacecraft will approach the sun to distances below 10 solar radii. So it's technologically just very advanced. And what is interesting here is that not only the bulk properties are measured with high accuracy, but also 3-dimensional distribution functions of ions, electrons, and alpha particles are also measured. So the wealth of measurements here just provides us with a lot of challenges from the simulation perspective. And I also mentioned the anisotropy of galactic cosmic rays. This is observation over there. The figure is the observation from the Tibet experiment. And you see that the anisotropy is small, but you see that there are boundaries over here. And the boundaries is very interesting. So if you look at this boundary, it appears that this is exactly coincides with the hydrogen deflection plane, the plane where formed by the velocity of neutral hydrogen pristine in the interstellar medium and measured by SOHA. So this other boundary is the plane perpendicular to the BV plane. And this red thing is exactly where the heliotail is in simulations. So this is a fantastic measurement. I will mention a few things about that. So just for the record, I give, as requested also in a template, I give you a list of our science funding, which is mostly NASA, but we also, in addition to PIREC, some of our NSF projects ended in the last year, but we still have this REU site project. The major accomplishments for during the past year, I mentioned many of them. First of all, we took into account the effect of pickup ions, and especially we found out fantastic, really important issues related to the application of the distribution, non-Maxwellian distribution function, in particular when you use a kappa instead of a Lorentzian distribution function, that it appears when calculating the intercollisional integral, it is important to take into account the dependence of cross-section, charge-exchange cross-section of energy when calculating the integral. If it's not, the integral diverges. But if it's, there are ways to fix it, but they are not physical. And we do this in a physical fashion now. We calculated time-dependent ENA fluxes. We used coronagraph images from SOHA and stereo spacecraft to simulate coronal mass ejections. We also used the Monchili-RG model driven by the Air Force data simulating photospheric flux transport model ADAPT to simulate solar wind properties at Parker Solar Probe. We investigated the effect of the Heliopools instability on the Voyager measurements of the galactic cosmic ray fluxes. We also derived the genuine anisotropy of tera-electron volt cosmic rays in the interstellar medium and proposed the source of the physical source of this anisotropy. The results were published in 7 papers, 3 more Ion Press reported, and over 20 meetings. This is our model of the solar wind, where we insert flux rope, which further expand, revealing coronal mass ejection. Here you see the radial velocity components, the sun at the center, and this is at different times after coronal mass ejection was born at the solar surface. And these are magnetic field distributions. So to do this modeling, we actually use the data. So the flux rope, which is inserted into the simulation, and this is the animation of this propagation of CME propagation in the temperature profile and then in the magnetic field. We use data sets. We use observations, and the observations are developed, multi-viewpoint observations. They are developed in a proper way so that the CME we insert, it behaves like it is indeed observed by remotely by different spacecraft. Observations we use, first of all, we use the graduate cylindrical shell model to find the speed, the tilt, and direction of coronal mass ejection. So these are 3 different viewpoints of the same CME, and we outline it to obtain the shape and velocity. We also calculate the true mass of solar plasma from 2 viewpoints of the stereo A and B white light coronagraphs images. We also used poloidal flux of coronal mass ejection, which is measured from the unsigned reconnection flux in the area covered, you see red line over there, by post-eruption arcade. And as a result, the result is shown here, observation, simulation, and comparison of the CME observed and simulated CME speed. We also calculated essentially the velocity we calculated is 812 kilometers per second. Well, it was measured, but the simulated in our case was 897. But we also pretty well reproduced the mass of plasma inside the CME and also the poloidal flux. Here I show you the solar wind simulations along the Parker. First the figures on the left. This is magnetic field and density at Earth, measured at Earth. And this is as showed along the Parker Solar Probe trajectory. We do not compare. Okay, we don't compare those because the data is not freely available now at Parker Solar Probe. But at Omni, you see that it's pretty nicely reproduced. These are the Heliopools. The boundary between the interstellar medium and solar wind is unstable, as I showed here. And you see the Voyager 1 trajectory at the points. We calculated the fluxes of galactic cosmic rays at those points. And what we obtained is shown in this figure on the right. And the figure on the left here shows that indeed before where the crossing of the Heliopools was pretty complicated, and the galactic cosmic rays, it's fluxes of all energies above 70 mega-electron volt. Instead of just simply increasing in a jump-like fashion across the Heliopools, there were increases and decreases of the flux. And we showed here in our simulations that these increases and decreases, they are related to the instability and Rayleigh-Taylor type. And the spacecraft was actually crossing the solar wind and interstellar medium several times. And for this reason, the fluxes was going up and down. This is TV cosmic ray anisotropy, which I mentioned. These are observations, which I showed you already. This is our simulation result, which fit the observation pretty nice. And this is the difference between them, which is the anisotropy, which is entirely due to the astrophysical reasons. We calculated the gradient of cosmic rays. It's 5 TeV cosmic rays. We calculated the gradient of the cosmic ray density and found that it is directed roughly in the direction of the Vela supernova. And we claim that Vela probably is the reason for this anisotropy. While performing these simulations, we also found out additional discontinuities existing in front of the Heliopools, Henning shock, and a tangential discontinuity over there, which is, should be discussed. You understand why blue waters was important, because it's already based on what I told you. I just only wanted to, before I end, to greatly acknowledge the support from all people on the Blue Waters team. And they pioneered an individual approach to users' needs. And we got help not only in code porting and scaling, but even occasionally debugging. And whether scheduling requests or visualization support was requested, we were always provided with exceptional help, professionally efficient manner. And so the experience of Blue Waters will help other supercomputer centers. And thank you guys from Blue Waters. And see you soon. It's not farewell. See you soon at other supercomputing and modeling conferences. Thank you very much.